Good morning, everyone. My name is Reid Prichard, and today I'm going to be talking to you about some comparison of numerical methods and validation of GPU-accelerated DNS in ANSYS Fluent. So first off, a little bit of background. Historically, DNS has been done using what's called the spectral element method. Now, the spectral element method allows the use of high-order, really efficient numerical methods, but there are some key limitations. First, it's challenging to incorporate additional models. The particular example that was a problem for us is fluid structure interactions, whereas other solvers like ANSYS Fluent have those incorporated already. Second, you're limited in your mesh. Spectral element methods do not allow you to use an arbitrary mesh. You have to use a structured grid. So that can make irregular geometries very challenging, requiring either a lot of blocking or maybe it's just not possible if a geometry is past a threshold of complexity. So finite volume methods, or FV methods, are useful for DNS. So this has been done before, but the high order methods that have been done in the papers we found require a structured grid. So that fixes one of the problems of spectral element methods, but it leaves that remaining problem of complex geometries. ANSYS Fluent remains completely unvalidated. Though there are some papers that claim to perform DNS on Fluent, there's little insight into what's actually going on underneath the hood and no proof that DNS is actually being performed. So our goal here is to validate ANSYS Fluent in DNS. Additionally, we're going to be using methods that are applicable to arbitrary grids, even though the particular physics we are modeling or resolving could be done using a structured grid. So why Fluent? Probably a lot of people in the DNS field will have this thought to start because it's certainly an unconventional choice. Well, Fluent is widely used in industry, and not everyone gets to choose the solver they use. Second, many undergraduates' first experiences with CFD are in Fluent, so there's a familiarity there that kind of gives an advantage to expanding Fluent's capabilities. Next, and importantly, Fluent has recently added a GPU-accelerated solver. So because CFD is so highly parallelizable, GPUs are perfect for that and promise to really enhance performance. So compared to a comparable CPU-based machine that had 120 Milan X CPU cores, and for those of you that aren't knowledgeable on the current hardware, this is essentially the newest high-performance computing hardware AMD has to offer. In comparison, a single A100 80GB GPU, which is one of the highest performance options from NVIDIA, has about half the hourly cost, and yet it provides several times the performance in our experience. So those two things are multiplicative, where at that half that hourly cost, it's going to get you your results several times as quickly. So that's a huge difference. And unfortunately, the GPU solver is currently full of bugs, very unstable, has given us a lot of problems, but despite that, it has dramatically reduced project costs. Okay, so before we get into the DNS results, let's take a look at Fluent's numerical methods. It's known that momentum discretization has an outstanding effect on DNS results, where you want schemes with really minimal false diffusion, because too much diffusion will smear out the really high frequency, low length scale fluctuations that are necessarily a part of DNS. Fluent offers 6 momentum schemes. So first order upwind differencing, or UD, second order upwind differencing or linear upwind differencing, central differencing, a bounded version of central differencing, and then quick and muscle, which are both blends of central differencing and linear upwind differencing. Now you might say, okay, well, I've seen comparisons of probably all of these methods, but bounded central differencing. What's the point of this? Well, Fluent doesn't necessarily implement the canonical versions of these methods. In most of the cases, they implement their own little tweaks to them, usually for stability. Plus, with Fluent being an industrial code and its source code not being available, we don't know for certain that what Fluent says they're doing and what they're actually doing in the code behind the scenes matches up, so it's good to compare these methods on Fluent itself. We haven't been able to find any work that thoroughly compares the diffusiveness of these schemes, so we will be doing that on 3 grid types, which you can see over on the right. We have a triangular grid on the top, a quadrilateral grid in the next one down, and then a polygonal grid on the bottom. We tested two sizes of each. You can see the grid that's 25 cells along each edge on the right, but we also tested a grid with 100 cells along each edge. And you can see the boundary conditions listed on those figures. So on the left-hand side, we have this velocity magnitude of 1, and on the top edge, we have a velocity magnitude of 2. In both cases, moving diagonally from top left to bottom right. And then on the outlets, we have, of course, this pressure equals 0 boundary condition. These grids were extruded one cell into the page because we wanted to ensure that there aren't any behind-the-scenes differences between Fluent's 2D implementations and their 3D implementations, but we'll still refer to these as, triangular, quadrilateral, polygonal, even though they're, wedge, hexahedral, and polyhedral. Okay, so let's take a look at the results on the quadrilateral grid. First, let's look at these plots on the right-hand side to just get some background on what they're telling you. So on this top left plot, we have on the x-axis the proportion along the normal. So moving diagonally in a cross-flow direction from the bottom left to the top right of the domain, we would expect to see this square wave, really a perfect shear layer, where on the one half of the domain we have 2 meters a second, and on the other half we have 1 meter a second. And this plot has a bit of the middle chopped out of it, just so you can see the dispersion and diffusion where it's most significant a little bit better. Here we just have the error plotted for the actual resolved profile versus that ideal square wave. And again, that's just so you can get a little closer look at what's going on there. We then plot the spatial derivative of that profile. So ideally, we would expect to see kind of a Dirac delta centered on 0.5, where the velocity derivative is infinity right on this square wave, and then it's 0 elsewhere. Lastly, we're looking at the velocity magnitude as you move in the streamwise direction from the top left to bottom right corner. So we would expect the velocity there to just be the average of the two inlet conditions, so 1.5 meters per second. Okay, with that background, let's take a look at the actual behaviors of the method. So in both cases, in this 25 by 25 grid and down in the finer grid, we see that central differencing and bounded central differencing exhibit the least diffusion. So they're closest to this ideal profile in both cases, and we also see that the gradient resolved is greatest in both cases. So they're closest to that ideal kind of Dirac delta type gradient. We see that in both cases, the maximum gradient resolved is 50 to 100% higher than that with really any of the upwind biased higher order methods, linear upwind differencing, muscle, and quick. We do see, though, that CD and BCD somewhat underpredict this centerline velocity. So by the outlet of the domain, they've kind of reached that optimal value or the correct value in the coarse grid, although they don't quite get there with the fine grid, whereas the other three methods do a better job of approximating that. It's a little surprising that bounded central differencing resolves sharper gradients than central differencing, because how Fluent describes bounded central differencing is that it'll, based on some boundedness criteria, the convection boundedness criterion, it will switch between central differencing, upwind differencing, and linear upwind differencing. So if UD and LUD are both more diffusive than CD, it seems like moving that direction would give you something more diffusive than CD. But what's likely going on here is that ANSYS implements a deferred correction scheme in their pure central differencing scheme, where they calculate an implicit upwind differencing first order term, and then they use an explicit correction term to hopefully recover that to central differencing. One would expect that in a steady solver with sufficient iterations that recovery would happen, but that's not what we found here. Now let's briefly take a look at the results on the polygonal grids. We won't talk about the triangular grids here just because despite having the element count when you convert from a triangular to a polygonal grid, we found that the polygonal grids were less diffusive and even less dispersive than the triangular grids. So from this consideration, there's really not a reason to use a triangular grid. On both the grids, the coarse grid on top and the finer grid on the bottom, we saw that again, the central differencing and bounded central differencing schemes produced the least diffusion, with this square profile being best approximated in both cases, and the maximum gradients resolved being the greatest. We did find that linear upwind differencing and muscle were not far behind, although quick was not considered due to not being applicable to a polygonal grid. We saw that again, central differencing and bounded central differencing underpredicted that centerline velocity, whereas the upwind bias schemes overpredicted by a little bit in the coarser grid and recovered a little bit in the refined. Now let's briefly look at the RMS velocity fluctuations in X, Y, and Z, where you can see the U component on top, V component in the middle, W in the bottom, and of course these are normalized by inner scaling, so W plus and Y plus here. You can see that in all of the cases shown, we have an excellent match with the validation data, with, compared to the mean velocity profile, less of a clear-cut difference between these different cases. However, you will notice that grid S2 still has the highest peaks here, and grid L1 is the next highest. So these again suggest that not only is grid S1's mesh length scale perhaps not small enough, but this suggests that the domain may not be large enough. Now let's look at the turbulence kinetic energy budgets. So you can see that the budgets match the validation data very well, even for the coarsest grid, grid S1 in the top right. However, you will see that dissipation is underpredicted from the wall toward the center line, with the largest magnitude of error near the wall, whereas the largest proportional error is near the center line, where you're looking at about 50% error there. We also see a deficiency in production here on grid S1, and in both cases, the velocity pressure gradient correlation in purple is a poor match, but we found this measure to be very sensitive to statistical variation, and limitations in the current state of Fluent prevented us from getting as much integration time as we would have liked here. While we see minimal differences between these two grids, S1 on top and L1 on the bottom, where again L1 is the same mesh length scale as S1, but it's doubled in the streamwise and spanwise directions, theoretically allowing resolution of greater length scales. We do see that the dissipation is a little bit closer here, and the biggest difference is in the production, which is now pretty much exactly on the validation data. So this suggests that grid S1 is not large enough to capture the largest turbulent motions. It's unclear why grid S1 wasn't able to pick those up, considering grid S1 has the same dimensions as our validation data's domain. Finally, let's take a look at some energy spectra. So the hexahedral grids, starting with grid S1 in the top right, generally agree with ABE, which is our validation data. You can see particularly in the spanwise direction, the U and V components are a great match, though the W component, while it's a good match all the way up to the highest wave numbers, shows this odd dogleg type error. In the streamwise direction, we see that there's a pretty noticeable underprediction of low wave number energy, though we will note that ABE's data still have a noticeable slope to them on their left-hand side, which suggests ABE's domain may not have been large enough, and that agrees with what we've seen on previous slides, where moving to the larger grid enhanced our production of turbulence kinetic energy. We see that in the streamwise direction, if we refine the grid moving to grid S2, we see that the low wave number energy has improved and now matches ABE. However, we see that the pileup, while it has extended into the higher frequencies, even in the intermediate frequencies, we are over-predicting energy by quite a bit there. In the spanwise direction, we've moved to the other side of ABE's curves in this plot, though overall it is a little more consistent with the odd error seen previously just in W, now replaced with a more uniform type pile-up look to the data. Grid SP in the bottom left, which again is our polyhedral grid, actually matches surprisingly well in the low wave numbers, where we see maybe even closer than grid S1 despite it being an unstructured grid. But we see this very odd, flat, jagged white noise in the high frequencies. This is similar to what we've seen when Fluent was unknowingly truncating our output data, giving a bit of randomness to the solution field. But we're not sure if what could be happening here is perhaps an aliasing error caused by interpolating unstructured data onto structured lines in order to produce these plots. Okay, as computing power is rapidly growing over time, complex geometries that were previously delegated to RANs or perhaps LES are now coming within the reach of DNS. These complex geometries unfortunately require the use of not only finite volume methods, but particularly low order methods, as opposed to the high order spectral element methods that have been used in the past. We found that characterization of Fluent's numerical methods is lacking, so we performed a study comparing the diffusiveness and dispersiveness of their momentum discretization schemes. Validation is a crucial step, so even though finite volume methods have been shown to work for DNS, we are performing the first study that actually validates the low order methods that can be used on an unstructured grid. We've shown that Fluent can produce reasonable results using these low order methods, and our next step moving forward will be to validate Fluent on a separated flow. Thank you.